that has more flexibility.
Okay, so following the first two exciting talks, we have yet another third exciting talk coming. Anand.
So thanks for inviting me here. So this is going to be about some joint work with Thomas Wittig, and it's in these archive papers if you want to look them up. So let me just get started by saying, so this talk is about a notion of verification, and I guess we already heard about one type of verification this morning, and this is going to be a slightly different model. But to really set the stage, let me talk about the classical world and tell you about NP and interactive proofs. So you can think of, so I guess we probably all have heard of the class NP, but just to refresh your memory, it has all these problems for which there exists an efficient witness that certifies that the answer is correct. So for instance, any poly-time computation is in NP because you can just give the transcript of the computation and that's your witness. But there are also many of these interesting optimization problems that lie in NP. And you can think of the class NP as sort of a game where there's a prover who's trying to convince you that the answer to the problem is yes, and then you are the verifier and you want to be convinced of the correct answer, so you need to make sure the prover is not cheating you. So so the prover will send you some witness, which is like a polynomial-sized classical object, and then you check it. And so the problem is in NP, if there's some algorithm the verifier can execute where it'll accept correct proofs and it'll reject wrong proofs. So that's NP. And then you could imagine taking this game and making it sort of more powerful by adding interaction between the prover and the verifier. Oh, and I should also maybe clarify one thing here. So the prover here is assumed to be all-powerful, right? So maybe unlike in Urmila's talk in the morning, where there the prover was sort of restricted to be computationally bounded, here the prover can do anything it wants, and only the verifier is computationally bounded. And often, I guess, people refer to the verifier as like King Arthur because he's bounded and the prover is the wizard Merlin. So you could imagine changing this model by adding interaction between the prover and the verifier. So the verifier might come up with a series of challenges and send them to the prover and get back responses and try to decide whether the answer to the problem is yes or no that way. Classically, it's sort of known that interaction increases the power of these proof systems. So there's this model IP where you have polynomially many rounds of interaction, say, and then you can really solve any problem in P space in IP. So any problem that can be solved in polynomial space. And I guess we believe that P space is a bigger class than NP. So that's one thing you can do. And then you could imagine further generalizing this model by saying, instead of just one prover that I interact with, what if I have more than one and I try to sort of play them against each other? So if one prover tries to lie to me, maybe their lie will be inconsistent with the lie given by a second prover. And so this is this model MIP, multi-prover interactive proofs. So here you have, say, 2 or more provers that are not allowed to communicate to each other, and then you get to send them challenges and receive responses and decide whether to accept or reject. So it turns out that MIP is even more powerful still. So MIP was shown by these authors to be equal to nx. So this is like non-deterministic exponential times. This is like the exponentially scaled up version of NP. So really this multi-prover interaction seems to add a lot of power. And another way you could view this result, well, it's not exactly equivalent. It took a fair amount of work to get from there to this one. But if you scale down the results, so you're talking about a multi-prover interactive protocol where the number of bits you exchange is only logarithmic in the instance size. So that's why I've written log n bit messages here. And that turns out to be equal to NP. So this is one formulation of what's known as the PCP theorem. So just to say what this means is saying that there's this NP problem. It has a witness that's polynomially big. And you, the verifier, can somehow check it by only exchanging logarithmically many bits with these provers. So it's like you're doing some spot check that can always detect errors in this witness. So this is really, this is a highly non-trivial result, and it's kind of surprising. So that's the state of affairs for classical proofs. But we don't necessarily believe that classical proofs can exist for all the problems we're interested in. In particular, this is a quantum computing workshop. So one problem we're very interested in is quantum computation, so BQP. And I guess it's not, we have certainly no reason to believe that BQP is contained in NP, so there may not be any efficient classical proof of correctness for a quantum computation. But there exists a quantum proof. So this is the notion behind the class QMA. So the class QMA is really just like NP, except now you're allowed a quantum proof and a quantum verifier that can read the proof and decide whether it's correct or not. So this contains BQP because you can use this construction due to Feynman and Kitaev to encode a sort of transcript of any quantum computation into a quantum state. And then you can check that state by measuring its energy according to a particular Hamiltonian. So this is the history state construction that we've heard about. And then also this class contains other problems that are independently interesting, I guess.
Sorry, but isn't the verifier's power, doesn't the verifier have BQP power?
Yes, indeed.
Murmur for that.
Right, OK, so this is kind of trivial in the same way that P being contained in NP is trivial. But I mean, later when we talk about putting QMA in other classes that have a classical verifier, this will be more interesting. Yeah. OK, so I guess the other point I wanted to make is that QMA contains more than just BQP. It also has this independently interesting problem called the local Hamiltonian problem, which is sort of given a Hamiltonian, decide whether it's compute its ground state energy up to some small, like polynomially small precision. And this problem is sort of believed to capture the difficulty of many problems in condensed matter physics. So it's independently interesting for that reason. So that's what quantum proofs can do if you have a quantum verifier to check them. What if you add interaction in the quantum world? What changes? So you could imagine taking the single prover model, IP, and adding quantumness. So the only sensible way of doing this is you need to allow for quantum messages and a quantum verifier. Because if either of those things were classical, then you would just be trivially equal to IP, I believe. But it turns out even with adding the quantumness in both the messages and the verifier, then your class is no more powerful than IP. So it was shown that QIP is equal to P space. What about the multi-prover model? So now here there are many things you could do. So there are many moving parts here, and you can imagine quantizing all of them. The model I'm going to consider here is where you give the provers quantum power, but you don't give quantumness to the verifier. So this is a class called MIP star, where the provers are now, they're still not allowed to communicate to each other during the protocol, but they can share quantum entanglement that they've agreed upon in advance. But then during the protocol, the verifier is classical, and it exchanges only classical messages with these provers. And so the first thing I want to point out here is that it's not at all obvious that this class I've defined should even contain MIP, because I'm granting the provers more power, which means it's easier for them to cheat. And so the protocols that were developed previously may no longer be sound in this setting. But indeed, it was possible to show that that they are sound, or modifications of them are sound. So in the scaled down setting where I have log bit messages, this class contains NP. OK, so I guess these results showed it for 3 provers, and now we know this also for 2 provers. OK, but that's just saying you can reproduce these classical results. Can you go further? So I think the question that's very interesting here is, can you use this class to check a quantum proof?
So question.
Yeah.
So if you're going to bring up MIPSAR, there is this devious thing inside that it's not known whether tensorable entanglement, if you're allowing infinite entanglement,
Yeah.
it's not known whether tensorable entanglement is equivalent to commuting measurement entanglement.
Yeah.
So which of those versions of MIPSAR? They should really just be 2 different complexity classes, actually, for the time being.
Sure.
Does this theorem that contains NP apply to both versions of MIPSAR, or?
I believe it does. I mean, I'm sure it applies to the tensor product model. I think, yeah.
Approximate
finite entanglement.
But you don't have a bound on how much finite entanglement. So there's still no upper bound on the tensor product version of MIPSTAR. Maybe this is what you're about to say.
No, I mean the tensor product model is not approximate within finite dimensions, and the result applies in the tensor product. Finite or infinite.
So for this notorious commuting measurement entanglement model, it's still open whether it contains NP?
Yeah, I suspect the result extends, but it hasn't been verified.
Okay.
Okay, so yeah, that was a great question. I guess for the rest of this talk, you can just assume the tensor product model. So when I talk about MIPSTAR, that's what I mean. And also maybe that raises an important point. So I said that these provers are allowed to share an entangled state, but I didn't specify any bound on how much entanglement is allowed here, right? So it could be arbitrarily large, and that's sort of part of the difficulty of dealing with this complexity class comes from this. So okay, but to get back to this question here, I guess what I'm asking here is really in complexity terms, does MIPSTAR contain QMA, right? Because QMA is a class of quantum proofs. And this would be sort of qualitatively interesting because the verifier here is classical. And you're only exchanging classical messages with the prover. So somehow you have to like command them to do some quantum task for you without ever holding a quantum object in your hands. So that's sort of the challenge here. And then also you'd be showing that this class is bigger than MIP, assuming that QMA is not equal to NP, which I guess is a safe assumption, we think. So in this direction, what could you sort of conjecture might be true? Well, you might conjecture that if you take the classical result, so this is what I showed 2 slides ago, that MIP with log-sized messages is equal to NP, and you just like stick a Q on both sides, that this might be true. So that if I take NP and convert it to QMA, and I take MIP and convert it to MIP star, that this inclusion would hold. I don't want to conjecture an equality here. And so this is a conjecture that is in a paper by Fitzsimmons and Vidic, and they called it the games quantum PCP conjecture, or the interactive proofs quantum PCP conjecture. Just for the reason that it's sort of a generalization of this thing, which is one variant of the PCP theorem in the classical world. Right, so this is the target we're going to be aiming at for the rest of the talk. So why would you want to prove such a thing? So I guess I mentioned these points earlier, but maybe it's good to reiterate them. The first thing is that if you showed this, then this would tell you something interesting about these protocols with entanglement. So this would show that, for instance, if I give you a specification of a protocol and you want to compute the maximum success probability over all strategies, that it's strictly harder to do this with if you look at entangled strategies than classical strategies, assuming assuming that QMA is not equal to NP. So that's sort of interesting because I guess people have cared about this question of computing the maximum success probability in these protocols. Another
You have to approximate to within a constant.
To within a constant, yeah. So yeah, I should maybe clarify on this slide. So far I haven't talked about the completeness and soundness parameters of these protocols. And when I don't mention them, I intend them to be constants. Like in the yes case, you succeed with 2/3 probability. In the no case, you succeed with at most 1/3 probability. So the second point I think is quite interesting, which is that again on this assumption that QMA is not equal to NP, you're trying to show that this class MIP star is strictly more powerful than MIP, which means that somehow you have to make use of the additional resources you gave the provers. So the provers in particular must share some sort of entanglement, in the honest case where they're playing according to the strategy you want them to use in your protocol. And this is kind of interesting because in other settings where you look at verification of quantum computation, you design protocols that maybe could be passed, like if the prover were exponentially powerful and it had an exponentially big classical description of the state that it wanted to simulate, it could just compute all the quantities you ask it to compute and and pass the test. But here, even that's not sufficient. Like even if the prover is arbitrarily powerful as a classical being, if it doesn't have this shared entanglement, it shouldn't be able to pass your protocol. So that's as qualitatively interesting and sort of different from the behavior you see in the classical world. And then finally, this point about BQP being contained in QMA is now might lead to something non-trivial, because then you would have a delegated computation scheme, perhaps, where the verifier or like the client remains classical.
But for BQP, don't you already have an MIP star protocol from this RUV that was mentioned before?
Yes. So okay, that's going to be on the next slide. So I'll tell you how we want to improve on that. I think it's the next slide.
Other.
Okay, so actually it's like maybe a couple slides from here. So I will mention it. So I guess just to clarify what the task is that we were doing. So I said I wanted to design an MIP star protocol for QMA. So that means I should take some QMA problem. So take this local Hamiltonian problem that I mentioned earlier, and I should design a protocol for that, say. So instances of this problem are described by Hamiltonians, right? And the answer is yes if the minimum energy of this Hamiltonian is below some threshold A, and it's no if it's above some threshold B. So I want to come up with a way to map a Hamiltonian to a protocol in such a way that if the energy is below the threshold, then the probability of success in my protocol is high. And if it's above the threshold, then the probability of success should be low. And then as I mentioned, you need to somehow use entanglement to do this. But also, now that you're allowing entanglement, you need to prevent the entanglement from being used to cheat you. And so here, you have to keep in mind that you don't know what the size of the entangled state is the provers are sharing it. So you need to somehow show that for whatever protocol you come up with, even if the provers share an enormously big entangled state, they can't fool you using that in some way. So how would you go about doing this? So really the key idea here that's used in all of the works in this direction is this phenomenon called self-testing that was, I guess, discovered almost in the physics literature. So it's going to tie into this thing I said about how you need to design a protocol that certifies entanglement. So it turns out that there exist games or interactive proof protocols where they have this very strong sort of rigidity property that in order to succeed with close to the optimal success probability, you must use not just entanglement, but some particular fixed entangled state. And so this is just defining what the primitive is. And on the next slide, I'll show you an example of this game. But you'd say that a protocol is a self-test for some state psi if you can succeed with high probability if you use that state. And if you succeed with close to the optimal probability, you must, the shared state between the provers must be close to psi. And so you have to be a little bit careful when you define what it means to be close to psi, because each prover could apply a local unitary rotation to their half of psi, and then you'd never be able to tell, right? But so what this means is that sort of up to this freedom of local unitaries or local isometries, the shared state must be close to psi. So does this notion sort of make sense? Is there any questions at this point?
What is this in the physics literature?
So the physics literature, this comes out of Bell inequalities. Although I guess this self-testing property was not maybe used in the physics world. It was first used by computer scientists.
Used in the CS literature early on with, there was this really long, I think it started with Yao and then,
Or like the Myers-Yao.
It does show up in paper by Reinhard Werner from the 80s studying QFTs, and it's actually relevant for them that they can.
So
maybe there were two different strands.
I think it was
independent strands.
quantum state or favorable particular quantum states, because I had thought that even Bellany, even showing that any Bellany violation holds is not known for arbitrary.
Indeed. So this is like, it's not known whether a self-test exists for any size. It's just for some particular size we're able to construct, favorable size. So I guess the example that's known is this famous CHSH game. So first I'll just briefly remind you some properties of this game. So this is really like a mild simplification of Bell's original Bell inequality. But you can think of it as like an interactive protocol where there's a verifier that exchanges, there's one round of interaction. The verifier sends one bit to each of two quantum provers, and it receives back a single bit. And sort of what was shown by Bell was that if the two quantum provers share this EPR state, so like a single E bit of entanglement, then they can succeed in this protocol with higher probability than any classical strategy could. So that's what Bell showed. And now the self-testing property, which holds for this game, is actually the following. So I said that well, maybe I didn't say this, but it's true that the optimal success probability in this game is something like 85%, which is achieved with this EPR state. And it turns out that if you succeed with probability like 85% minus delta, then the state you share has to be close to this EPR state up to error square root delta, up to local isometry. So this is a protocol that you can use to test that there's one E bit of entanglement between the two provers. And you might be annoyed by the 85%, but you can also design a test with perfect completeness with a different game called the magic square game. But I'll refer to CHSH just for simplicity in the rest of the talk. OK, so I guess I've introduced this notion of self-testing, but only for a very simple state, right? Like the single EPR state. And what I really wanted to do was design a protocol for a QMA complete problem. So this suggests a sort of strategy, which is I want a protocol that's a self-test, but not for the EPR state, but rather for the witness state of my QMA problem. So if I take local Hamiltonian, I want to design a self-test for states of low energy according to my Hamiltonian. And so this is indeed the idea that was, I guess, like implicit in this work by Reichert, Unger, and Masrani. So they were able to show by sort of applying many copies of the CHSH test that there is indeed an MIP star protocol for QMA where the number of bits of communication between the verifier and the provers is polynomial in the instance size. Because you have to sort of do polynomially many repetitions of this CHSH test and apply some statistical analysis to the outcomes and so on.
There's nothing self about this self-test, right?
I guess it depends what you mean. I don't know why it's called a self-test. I guess the idea is that a state is certifying itself only through measurements on it, but yeah. It's sort of an obscure term. Maybe someone else knows the history of it.
Testing of the self by others.
OK, so then I guess there was subsequent work in this direction. So this protocol was an MIP star as I defined it with like this constant completeness soundness gap. Now it turns out that sort of if you relax that requirement and you allow the gap to be much smaller. So in the yes case, I succeed with some probability C, and in the no case, I succeed with probably at most C minus an inverse polynomial. So Fitzsimmons and Wittig discovered this protocol with quantum messages, but only like log size messages that achieved that could solve problems in QMA. And you can think about this as sort of instead of so this RUV thing applied sort of something to check every qubit in the state that they wanted to characterize. And now here, instead of checking every qubit, because you're not requiring this gap to be so big, you can just check a few qubits.
Maybe I don't know how to read the first equation.
Uh-huh.
So that's polynomially length, the thing RUV13.
Yeah.
Polynomial length messages to the provers,
Yes.
or back and forth with the provers. Completeness 1, soundness 1/2.
That's correct, yeah.
And just simply by ignoring all but one prover, isn't that the same as IP? Or do I?
Ah, I see, yes. So I guess really the application they wanted this for was really they could show that any MIP star protocol with quantum messages could actually be done with classical messages. So that's something that does not follow from known complexity results. But like in particular one.
So that's a human, not MIP.
Or like on the left you could even put QMIP.
But also,
is what follows from there.
So the honest provers didn't have to be more powerful. They didn't have to be infinitely powerful.
Ah, right. Yes, that's correct. So that also held in their case for BQP. I guess that's another good feature of this result.
In extracting part of the point you're making from RUV, you just wrote something a little bit too weak because IP is in between the left side and right side as stated, and then IP
Yes.
Okay.
Indeed. Yeah. So this statement does not capture all the good qualities of their result. Yeah.
So, yeah, just to understand the setting, who holds psi? I mean, the two provers just share like a bunch of EPR pairs, and one of them also has psi. Is this how the way to think about it?
Yeah. So this actually differs in the different protocols. So in this protocol, I think it's something like that. So they hold a bunch of EPR pairs, and then in the course of the protocol, they will prepare psi by their EPR pairs gives them like some resource state, and they'll prepare some version of psi. In these later protocols, there's a different way of doing it where you sort of encode psi with an error correcting code and distribute that amongst the provers, which if I have time at the end, I'll show you how that's done.
But if you're non-BQP, then just preparing psi by yourself might be hard, right? And you want
indeed.
it to be efficient, right? So like it needs to be given in some form.
Yes. Yeah. So but in all these protocols, if you're given a copy of the ground state, then you can prepare whatever state you need to do the protocol, I believe. Yeah. Certainly for the ones after RUV, I think that's also true for the RUV protocol. Okay, so this was for quantum messages, and then the subsequent work by Zhengfeng Ji showed you could also do sort of the same thing with classical messages. So maybe it's best to compare these two things. So we started out by saying, there's this protocol for QMA with polynomial-sized messages, but it has the completeness soundness gap you'd expect. Then here's another protocol where you have only log-sized messages, but the gap is small. So you need to repeat the protocol many times to really be confident of the answer. And what we want to do is like get this, but with this gap. So the completeness soundness gap should be a constant with only log-sized messages. And I haven't explained how exactly, but somehow all of these things are based on tests for EPR pairs. And in order to improve this gap, really what's needed is a test for many EPR pairs where the completeness soundness gap of the test does not depend badly on the number of EPR pairs you're testing. Yes.
Can you say a bit more about how you connect the test of maximum entangled state to the test of the general history state, or?
Sure. So I can maybe draw a diagram here. I think I have or actually, let me skip ahead to the slide that does this, just because it has a picture. Right. So it's going to be something like, in general, this history state, what we're going to do to it is encode it with some error correcting code. Like say this code encodes every qubit into k qubits, right? So then there'll be k provers, and we'll distribute it amongst the k provers. And then you can sort of lift a test for EPR pairs into a test for code states by sort of using the fact that if you partition this into one prover and the other 6, and you think of these, so here I guess I've drawn 7, but if you partition this into one prover and the rest, the state across that cut looks like an EPR state. And then you can apply the EPR test to every cut, and then by doing that, you've certified that the state is encoded the way you want it to be. And then once you have an encoded state, you can then command the provers to do things like measure logical operators, and that's how you extract the energy of the witness state. Okay, so let me back to where I was. Right, so I guess if that was sort of for experts. If you didn't follow, that's okay. The main point is that somehow there's these known strategies for lifting a test for EPR pairs into a test for a QMA witness state. And really, it seems like the technical challenge was to design a good test for many EPR pairs. So I guess that brings me to sort of the main result is that, yes, this is indeed possible. So we're able to design a two-prover protocol where you can test that the provers share n EPR pairs using only log n bit questions and answers. And the completeness and soundness errors don't depend on n. So it's just, they just depend on the error to which you want to test the state. So if I want to test that the state is epsilon close to n EPR pairs, the soundness is like 1 minus some polynomial in epsilon, independent of n. And then if you take this test for EPR pairs and you plug it into this framework that I'm not describing, you can turn it into a protocol for testing these ground states as well. So you can get so this result I had to phrase in a sort of strange way because there's like a randomized reduction going on in here, but you can at least show that it's QMA hard to estimate whether the success probability in a given MIP star protocol is greater than 2/3 or less than 1/3. So this is sort of close to this statement that I said was our goal, which is just putting QMA directly in this class by giving a protocol for it.
And what's D?
Oh, D is just some universal constant that I haven't computed. So does the statement of this result make sense? Okay. Yes.
What do you exactly mean by randomized reduction here?
So the randomized reduction is something like, given a QMA problem, so you're given a Hamiltonian, you can construct a protocol out of it, but the mapping from the Hamiltonian to the protocol is randomized. So it's like you apply some BPP computation to the description of the Hamiltonian, and you get out a protocol.
Actually,
Yeah.
sorry.
Go ahead.
Can you clarify the connection between the error and the soundness? Like, what exactly do you mean by tested up to an error epsilon and then?
Oh, I just mean that like if you succeed with probability greater than, maybe it's better to invert this. So if you succeed with probability greater than 1 minus delta, then you know that the state that's shared by the provers is like delta to the 1 over d close in this metric I talked about earlier to the NEPR state. So like if you want to, for instance, like your end goal is probably going to have epsilon be some small constant. And in that case, this will also be some constant that comes out of that. OK, so the protocol that we actually design here is a little bit complicated. And I'm going to tell you about a simpler protocol that achieves sort of, it doesn't achieve quite the, so it's less efficient in terms of communication. So it involves sending more bits between the prover and the verifier. But a lot of the ideas used in analyzing this protocol are similar to the more efficient one. And so this is what we called the Poly-braiding test for reasons that'll maybe become clearer when I talk about the actual test. But let me just tell you what the parameters are. So it's basically the same sort of thing as on the previous slide, except instead of log n bit questions, it's n bit questions. And so I think when we were coming up with this result, it's sort of like there were two parameters that we cared about, right? It's the efficiency in terms of number of bits communicated, and also this soundness error. And it seemed like I guess the pathway we followed is first to like achieve this good soundness error at the cost of poor communication efficiency, and then improve on the communication. And so why is it called the Poly-braiding test? Well, it involves asking it involves sort of testing that the provers are applying measurements from the Pauli group on their state, and it involves like checking in particular some highly non-local measurements. So I'm going to show you what the measurements are in a second. So let me remind you first of all of a few facts about Pauli matrices. So the Pauli matrices, they all so I'm only going to talk about X and Z in this talk. I'm not going to mention the Y. So these are two matrices that act on, say, a single qubit. So they're 2 by 2 matrices that square to identity, and they anti-commute. So xz is equal to minus zx. So that's like the single qubit Paulis. And I'm going to introduce this notation for tensor products of these. So I'll say that like an n qubit Pauli x of A is going to be the tensor product. So A here is going to be a binary string, and x of A will be the tensor product that consists of Pauli x acting on all the locations where A is a 1, and identity acting on all the locations where A is a 0. And similarly for Z. So now these things satisfy, you can just like, this is almost just notation. So they satisfy some relation. So if I take the product of two x's, sort of, if on any particular location, if I have two x's, they'll cancel out and give me identity. So that's, and if I only have one x, I'll still have an x. So that can be captured by saying that x of A times x of B is x of A plus B, where this addition is mod 2. And then likewise for the Z. So this is just like lifting these two relations to this many qubit notation. And then if I try to commute two of them past each other, I'll get a -1 for every location in which there's both an x and a z. So that's saying that x of A times z of B is z of B times x of A times this phase, which is -1 to the inner product between them. So these are like some algebraic relations that characterize what the Paulis do. And then there's another nice fact about these Pauli operators is that they can characterize the EPR state. So if I have some state with the property that, say it's a bipartite state on 2 qubits, and it's preserved by x tensor x, or I guess 2n qubits, and it's preserved by z tensor z for all of these choices of A's and B's, then the state must be the NEPR state. So this is just, if you're familiar with the stabilizer formalism, this is just saying that these operators are like the stabilizer group of the EPR state. So now that I've introduced these facts, let me tell you how we use them in our test. So remember, our end goal was to check that the provers share these EPR pairs. And so we're going to use that last fact to do this by asking to measure all of those stabilizers, this x of A tensor x of A and z of B tensor z of B. So in order to do that, we need to first check that they're actually measuring a Pauli operator on some qubits. And that we do by checking the relations I wrote down on the previous page. So the first relation was that when you take the product of two x's, you get another x. And we're going to check that as follows. We're going to ask one prover to measure both x of A and x of B for some A and B on their half of the state. And then we're going to ask the second prover to measure x of A plus B and then some x of C for some randomly chosen C. And the purpose of the x of C is just to confuse them so they don't know, which of these things is supposed to be x of A plus B, so to make the distributions of queries look equal. And then we just check. So first of all, this is a measurement that they can do because all the different x's commute with each other, so you can simultaneously measure them. And then we just check that this relation holds, so that the outcomes that I get here, if I take their product, should be equal to the outcome that was reported for x of A plus B. So if you're familiar with the classical literature, this is really identical to a classical test for linearity of Boolean functions. And we're just applying it to the measurement outcomes of these x operators. Now the second relation I wrote on the previous slide was the same thing for z's, and so I can do the same test for z's. I just ask the provers measure a z in this way and tell me the outcome, and I check that the products are correct. And the third relation was this phase relation, right? So I said that x of A and z of B either commute or anti-commute depending on this inner product. So the way I'm going to check that is just use the CHSH game, which I mentioned a while back. So what I'll do is I'll just pick an A and a B such that x of A and z of B are supposed to anti-commute. And then sort of the thing is that when they anti-commute, they really behave like operators on a single qubit. So I can somehow just ask them to play the CHSH game, but using these two operators instead of whatever single qubit operators they'd have used in the CHSH game. And it turns out you can show that if you succeed in this game, the operators you use have to be close to anti-commuting. So that's the test that verifies that relation. OK, and then finally, I've checked all these relations that I said that the Paulis have to satisfy. I need to finally check that this last thing, that the state is stabilized by those Paulis. So the way I do that is I just ask the provers, ask both the first and the second prover to measure the same thing. So they either both measure some x of A or some z of B, and I just check that they get the same outcome. So this implements this last equation I wrote, and then this is supposed to tell me that the provers are indeed sharing an EPR state. OK, so these are like the 4 components of the test. The question.
So there's a variant of a fellow traveler of CHSH, which is the Paris test, which uses 2 Bell pairs,
yes,
maximally entangled Q quads rather than Q quads pair rather than, and it has the property that it has several properties. One is that the completeness is 100% for the test, and another is that it just directly uses multi-Pauli operators rather than superpositions like that. So I'm wondering whether a Paris version of your idea would
yes.
prove a better theorem, but might give you a cleaner theorem.
So indeed, we actually do use that. So I'm only using CHSH for the slide because it's too complicated to write the actual operators that are used in this like Paris magic square game. But like indeed, we actually use the
magic square. I was calling it Paris.
I guess, yeah. I think they call it the magic. Well, it's based on the magic square in some sense. So if I'm thinking of the right thing.
So it's due to Paris originally, but has a sort of physics setup, and then Mermin picked it up and set it up as a game. There's a few.
Well, Mermin didn't even write qubit with a U. I thought of Paris as being defined in sort of additive code terms, which is more to the point of why it's valuable. But okay, you actually do it that way instead in your paper, so fine. Okay.
Right, so that's for instance necessary to get, because I claimed perfect completeness for my test a few slides ago, and you need it to achieve that, because as you pointed out, that achieves perfect completeness, whereas CHSH does not. But for the purpose of the slide, I mean, you can just think of this as any sort of test that certifies a single qubit or maybe like 2 qubits of entanglement. It's really all we're using it is to check this phase relation between 2 Paulis, and any game that does that would be fine. Okay, so these are the 4 components of the test, and now I have to tell you why this works. So I just told you, I claimed that these are some relations that the Pauli operators satisfy, and then so therefore you should, and I said these are like checking these relations, but it's not clear that you couldn't satisfy this test in some other way. So why does this test even work? So let me give you a very high-level sketch of the proof. So the first thing that I have to say is, so I guess on the previous slide it was clear that if I really perform the measurements that I was supposed to do, I will succeed in all the tests with probability 1. Now I have to work sort of from the converse statement, right? I know that I succeeded in the test with probability, say 1 minus epsilon, and I have to deduce some consequence about the measurement operators that were used. So the first thing I can say is, it takes some algebra to show this, is that if you have some operators which I'm labeling x of A and z of B, but I'm not claiming that they're Paulis yet. They're just some things that have been claimed to be Pauli operators. But if they succeed in the tests on the previous slide, they must satisfy those relations on the shared state up to some epsilon, where epsilon here is related to your success probability in the game. Okay, so that's step one. Now, the second step is sort of the magic step, which is that I have a bunch of operators that look like Pauli's up to some epsilon, and now I have to use this rigidity property of the Pauli group. So it turns out that if you have these x of a and z of b's, you can round them to another set of operators, which I'm writing curly x and curly z, that exactly satisfy these relations. So maybe I'll not say that yet. So and then I said with error independent of n. So that means that I'll take this x, and I'll say there exists a curly x that's some delta away from x, where delta depends only on epsilon, not on n, such that these curly x's and curly z's now obey all these equations exactly, and they're still close to the original x's. So this second step is really what's characterizing the strategy used by the provers. It's saying that in order to succeed in this game, they had to use measurements that were close to some set of things that behaves like the Pauli operators. And this is, I guess, appeared in more general settings. So this is sort of, you can understand this classical linearity test that I mentioned earlier as showing the same statement over the group Z2 to the n. So, and I guess this is actually now known for any finite group. So this is shown by Gowers and Hatami, that if you have any set of matrices that sort of approximately satisfy the multiplication relations of the group, then there's a way to round them to another set that exactly satisfies those relations. So it's an exact representation of the group. And then the final step is that the Pauli group, sort of we understand the representations of it. So really, like, there's only one non-trivial representation, again, ignoring issues of like what to do with the y and whether to use plus I or minus I and so on. But there's sort of a unique irreducible representation that obeys this phase relation. And so when I put this all together, this implies that these things that were claimed to be Pauli x's and Pauli z's really are close to Pauli x's and Pauli z's. Then finally, from the fourth part of the test, which is this consistency thing, I can say, well, now I know that the state is close to being stabilized by honest Pauli spin matrices, and therefore it's close to the EPR state. So maybe I'll just say at a very high level what's going on again. So we wanted to test the state. The way we did it is in a two-step procedure. We first tested a number of measurement operators that the prover was supposed to act with. And we checked that they satisfied some algebraic relations. And then using that, we characterized the operators. And then from characterizing the operators, we can characterize the state that they act on. OK, so that's the analysis of this test. And so the analysis, the more efficient test I presented earlier is sort of similar, except you need to, instead of using all the Pauli operators, there's this special subset that we have to find that comes out of a classical error correcting code. But I don't think I have time to say anything about that. So I guess I'll conclude by saying a little bit about applications of this test for EPR pairs and also maybe some open questions. So I'll start by saying, first, if you just take, so I mentioned that BQP is contained in QMA, and so if you just take this idea and implement it in the most straightforward way, so you take our protocol for QMA, you can also get a delegated computation scheme for BQP that has sort of the following properties. So it's like it'll have a large number of provers, so it'll have it turns out 7 provers, but the verifier is classical, and it only needs to exchange classical messages with these provers, and it can be confident in the answer to any BQP computation. And furthermore, the provers are efficient, so they only need the power of BQP, because they only need to prepare this history state for the BQP computation they're trying to certify. So this result that we showed is in sort of a model called the post hoc model, where the provers first learn the circuit they're supposed to delegate, and then they are allowed to get together and collude and design their strategy, and then you separate them and you run the protocol. And that's needed for them to prepare this history state. But later work by several people who are here, so I guess Coladangelo, Grillo, Jeffrey, and Vidic, were able to use our tests in a sort of better way to obtain sort of almost optimal delegation protocols. So you can delegate BQP, and you can delegate a circuit that contains, say, M gates using resources, so like bits of computation and rounds and so on, that scale with almost linearly in M. So that's one application. And the other application I mentioned earlier was showing QMA hardness of this class MIP star. And so I won't say it again, but maybe I'll just review how we go from EPR pairs to this. So basically what we do is we want to actually test this QMA witness state. And we do that by encoding the QMA witness state using an error-correcting code. So this idea is, by the way, due to Fitzsimmons and Vidic. So the code is just like a single qubit code. So there's, for instance, codes that encode 1 qubit into 7 physical qubits. So you could take such a code, and then we set the number of provers to be equal to the number of qubits in this code. So if I work with the 7 qubit code, I'll now have 7 provers, and I'll distribute for each qubit in this witness state psi. I'll encode it into 7 qubits and distribute one of them to each of the 7 provers. And then one can apply sort of these lifted versions of this EPR test to check that the 7 provers are sharing a valid code state, and then also to command them to perform Pauli measurements. And then sort of Pauli measurements are sufficient for checking the energy of the encoded state. And then that's what you do to verify that this witness is a valid witness for a QMA problem. So in putting it all together, it would be, the overall protocol for QMA would be something like, with half probability, you check that the shared state is a valid code state by doing this EPR test on some partition of the provers. And with half probability, you ask all of them to implement some logical measurement of the energy. OK, so I'm going to conclude by mentioning some interesting open problems in this area. So one thing that I think is very interesting is that, so I guess now we sort of know that MIP star is more powerful than MIP, but there's no upper bound on MIP star. So this is related to the issue that's been mentioned of how there's no upper bound on how much entanglement the provers could have to use. And so one thing you might ask for is protocols that require the provers to share, ever increasing amounts of entanglement. And so maybe you could get stronger lower bounds in MIP star this way. And indeed, in the regime where the completeness soundness gap is very small, we know that this phenomenon occurs. So there are these results of Zhengfeng Ji, and then this follow-up work that came out recently that shows sort of by some sort of compression procedure where you take a protocol and you compress it, and then you scale up again and you compress it again, that you can get like much stronger lower bounds as you shrink the completeness soundness gap. And so I think a very interesting question is, can we use any of the tests that I described here to achieve similar lower bounds without shrinking the completeness soundness gap as much? And it turns out that if you could improve these compression results by even a little bit, then you might be able to show, I guess you would be able to show that MIP star is undecidable, which would be, I think, quite interesting. Another set of applications you could consider is, shared EPR pairs are very useful for cryptographic tasks like quantum key distribution. And there's also like applications to delegated computation that I mentioned, but is there more we could extract from our results? Something I want to think about. Then finally, this is a point maybe for experts here. So I mentioned that the conjecture that I was working towards is this quantum games PCP. There's another thing that's been called the quantum PCP. I guess this is actually older in the literature. And this is a generalization of a different formulation of the classical PCP theorem. So there's other conjectures about whether it's still QMA hard to estimate the energy of a local Hamiltonian up to a constant rather than to an inverse polynomial. And so it was sort of not known whether these two things were related in any way. And one consequence of our work is an implication from this other quantum PCP to the game's quantum PCP. And I think it would be interesting to go the other way. So this would be sort of like, classically, there's a nice connection between constraint satisfaction problems and these interactive proof protocols. And this would be developing the quantum analog of that. So how far can we go in both directions? And finally, the protocols I presented are all totally unrealistic in the real world, in the sense that they demand that, unrealistic in a world without fault-tolerant quantum computation. So they demand that the provers should apply some highly non-local measurement, like say measuring a Pauli on n qubits, and they should do this very precisely. So we don't tolerate, even a small constant error per qubit would be enough to make the provers fail in our tests. So it would be interesting to see what guarantees we can get on a test that could be that a near-term quantum device could succeed at. Probably you wouldn't be able to get something as strong as what we have, but it would still be, I think, interesting because it might be implementable in the near future. There may be some more speculative questions. So there's a connection between this class MIP star and a conjecture in operator algebras called Kahn's embedding conjecture. So in particular, if Kahn's embedding conjecture is true, this implies that the two-prover version of MIP star is decidable. So if you showed undecidability for two provers, then you would have disproved Kahn's embedding conjecture, which is maybe not such an unreasonable thing, because at least one operator algebrist has said that he thinks it's false. Another interesting question, I think, that's sort of related to this connection between protocols and constraint satisfaction problems is coming up with more complete problems for QMA. So right now, when we think about the class QMA, we really have to think only about local Hamiltonian. Like, we don't really have, I mean, there's some other problems, but they're not as many as in the classical world, where there's a whole variety of NP complete problems, and we have techniques for manipulating them that are very useful. And finally, there's this notion of self-testing that I mentioned, and we applied it only to this very, I guess, as Greg said, favorable state, the EPR state. And it's a very interesting question to see what other states you could test. And in particular, can you test not just states of qubits, but these continuous variable states that I guess experimentalists are actually preparing in the lab. And finally, in the analysis of the test, I mentioned that we use some properties of approximate representations of groups. And you can think about our more efficient test as sort of a sparse test for the Pauli group, for representations of the Pauli group, in that we're asking the provers to certify that their measurement operators satisfy some small subset of relations of the Pauli operators, and that's sufficient to conclude that there's an entire representation of the Pauli group in their Hilbert space. And I think it would be interesting to see what other groups you could do this for. Is there a general notion of group representation testing where you only check a small subset of the relations? That's all I had, so thanks for listening.
Questions? Let me start with a question. I actually have some. So for example, is there hope to do self-testing for bound entanglement states? Is that even a reasonable question, or?
I'm not sure. I don't know how the bound, the fact that entanglement is bound will make it harder to do the self-test. I guess the thing is that we've been really focused on the EPR state in particular, or at least when I thought about this. So I don't really have a good intuition even for non-EPR states, whether you could test them, even if they're not bound. So yeah.
So you can't write those as bound states if you or you
I think so, but I don't know. Right.
Well, I guess I have a comment and a question. The comment is, if the Kuhn embedding conjecture is false, and since we don't know that it is true, I would really recommend giving these two different flavors of MIP star different names. It's just too confusing. And in fact, there is a paper in the literature that just states that it's recursive. And I asked the authors about that, and they said, well, that's assuming the conjecture, that's assuming the embedding conjecture.
Mm-hmm.
So, but I think you just have to have two different names for these classes for the time being, maybe forever. But then the other comment I have, the question I have is, when you say that you're speculating that you could disprove the embedding conjecture, is that using one of these group representation methods?
I guess not directly. So the path that I was referring to is sort of using these compression results. And so the way they work is it's sort of like applying a history state construction to an MIP start protocol. It's like you start with an MIP start protocol and you want to compress it so you compress it in the sense of reducing the message length. And that's done by, you create a new protocol where the new provers are supposed to share some sort of history state of the original MIP start protocol, and then the new verifier checks that this history state is correct. And then the idea is that you would be able to recursively apply this compression by like, you compress and then you scale up the protocol and then you compress it again, and then you could get stronger lower bounds. That's sort of.
It doesn't completely resolve the matter because it's not clear to me whether this oscillating compression thing has a group theory engine inside using something like multi-Pauli's or other groups.
Well, I think there is sort of group theory in the test for the state. Like so the test for this history state of the MIP star protocol is going to be based on these tests for Hamiltonians, or similar to them in some way, and it will involve asking the provers to measure Pauli's and certifying that they're correct. And I think I would say that the only way we know of like testing these Pauli's goes through group representation, like this representation framework of the Pauli's implicitly.
So I'm not sure if it fits together into an obstruction, but what concerns me, I'm not completely sure whether it's a special case of the conjecture or a close analog for groups, which is the conjecture that all finitely generated groups are, or maybe all groups are so-called hyperlinear. And that is related to this notorious thing. An even stronger conjecture is that all groups are sophic. And the group theorists are having tremendous difficulty finding a counterexample even to that. So, if you want to be skeptical of the conjecture in this group theoretic setting, then there's an even stronger conjecture that some people feel like being skeptical of, but then it's been extremely difficult to find conjectures even to that, counterexamples even to that thing. So it would be, let's say, dramatic if quantum information gave you new tools for these group theory problems.
Right?
Wouldn't be the first time, I think.
Maybe you'll succeed.
missed the
It would be very dramatic.
With this note, let's thank Anand for